On behalf of Web-Based Solutions, I would like to welcome all of you to our today's webinar, Applied Data Science and Big Data Analytics Overview. Quite a mouthful, isn't it? So this presentation is allocated 2.5 hours, so it will be kind of a long journey. We will do a short break after the first hour, and maybe after the second, for 5 minutes, so that you can stretch your legs and grab coffee or attend to maybe some urgent matters. I would like to make this presentation as interactive as possible, so just fire off your question, put your question in the questions pane. I won't be keeping my eye on the chat, so the questions, whenever you would like to ask it during the presentation, just put it in the questions pane. Right. We will also have a Q&A session at the end of my presentation, and if a particular question would require some more time, I don't want to interrupt the continuity of my presentation by answering a very kind of a long and difficult question. Hopefully I would be able to answer it. But if a question just requires immediate clarification and I see a value in this answer, I will take the question right off. Again, Q&A session would be at the end as well. My name is Mikhail. I'm the Director of Curriculum Architecture at Web-Based Solutions, a consulting and training company based in Toronto. Our company has been providing a broad spectrum of regular and customized training in programming, system administration, big data, architecture to our clients for over 15 years. And a couple of courses related to the topics we are going to discuss today will be given to you at the end of the presentation. Okay, so I guess that's pretty much the logistics. So let's get started. Let me just set up a couple of things first. Okay. I don't want to preach to the converted, so if you're familiar with all those fundamental things or data sciences and other things, just bear with me. I have to cover those. We will go into more technical details later on, but let me just explain, kind of set the backdrop, so to speak. So data science, it's kind of a new kid on block. It's a new way to describe some of the activities that people have been doing, being business analysts, maybe data practitioners, or whatever the current title you have. So essentially, it's about extracting knowledge and business insights from data. Right. So there is much more than just being someone who knows how to work with Microsoft Excel spreadsheet or maybe some other tools. Right. There is more to it. And in this talk, I would like to maybe touch on some of the topics that are related to data science. It's a big, vague term, and there is just so much to it that definitely the time allocated to this talk is not enough, but at least we will kind of set some of the kind of boundaries. So data science is about statistics, pattern recognition, machine learning, data warehousing, data engineering, data visualization, and what's not. A very nice slide which puts together all those activities, skill sets, disciplines. So data science is at the core. It's kind of a moniker. It's a big term which can only be explained by going around it, starting with data engineering. I would say it's probably one of the closest to everyone's interest and job. And scientific method. Scientific method is all about having an algorithm of approaching your problem domain and finding a solution. So you need to have some background in math, statistics. Advanced computing, it's more about, not so much advanced. Computing in itself, it's an advanced topic. It's a skill that is really advanced. But it's more about maybe clustered computing using systems like Hadoop, MapReduce. Visualization helps you to get your message across. One picture is worth 1,000 words, right? Hacker mindset, I would kind of make this bullet as small as possible, because it's really doesn't sit very well with lots of folks. Kind of, how can I be a hacker if I kind of work on a large enterprise company? It's hackers should be somewhere, right? Another jurisdiction, not here. But it's all about scientific method. So those things are related, in essence, right? Scientists are hackers, pretty much. Domain expertise, that's what helps you to differentiate garbage from value in your data. Okay, so all that makes data science. I'm not going to kind of read the slide. I guess slides are more for your reference if you would like to revisit it. And we have uploaded the PDF, the electronic copy of this document to the handouts section, so you can grab it. If you cannot do that in the chat window, there should be a link to the document. Okay. Thank you, Carling, for providing all that information. So data science, again, can be described as data mining as something that people might refer to as kind of doing business analytics on your data. Right, but more and more people agree on a couple of things. First, data science places much less emphasis on infrastructure, on the ceremonial type of things, right? It's not necessarily be a very kind of expensive and very capable product from a known vendor, kind of all app type of systems, but it's more about open source products and tools which are currently proliferating, and it's just a matter of matching your problem domain with your use cases and select the right tool. Right, so you can use also the cloud. It's another venue for you to quickly set up your experiment, your sort of research project, if you will. Who is a data scientist? It's a practitioner who is essentially has all or maybe some of those skills that we saw on one of the previous slides. It's not possible, of course, in a sane mind to cover all those topics, right? So don't be hard on yourself. And I wouldn't say that there would be anybody who would say, yes, I know all that stuff. I know math, I have a hacker mindset, I have kind of domain expertise and what's not. It's more about, if you remember that webmaster type of role back in last century, right? So that webmaster was essentially someone who knew the Linux command line, CGI, maybe a little bit of HTML, and that guy was essentially wearing lots of hats, just trying to just do the business on the internet. Eventually, this role was, I guess, factorized into like front-end development, back-end development, system administration, DevOps, and what's not. The same thing happens here. So organizationally, that data science should be structured as a group of people who are working on a particular project. It might be 3, 5, maybe more people. And people have different backgrounds. So there would be a business analyst who knows the problem domain. There would be people who are very well versed in massively parallel processing systems. Others would be familiar with maybe functional programming, be it Python, Scala. And those people would make up a team who would work towards achieving a particular tactical or strategic goals in your data mining projects, right? There also should be someone who would be able to communicate all those findings, all the kind of nuggets of information that we have found to the stakeholders. It's very important. It's a combination of various things. And Jeff Hammerbacher, who used to work at Facebook a while back, he just, in one of the interviews, he summarized this as what they're doing, so that their data science at Facebook as a group worked on a number of projects, and then on any given day, they pretty much multitasked. So they worked in Python, they did some statistical experimentation, worked with R. Hadoop, they already had Hive at this point, I believe. I'm going to talk about Hive and R and Python just shortly. But generally, as you see, I'm going to repeat this theme again. It's not about a particular system that you have to learn. That's what I've heard on a number of occasions. So which system should I learn to become a data scientist? Is it R? Is it Python? Is it Scala? Or what? I would say there is no answer to this. It's more about and as opposed or, right? It's not kind of a, as it used to be, like, is it like Microsoft, or is it the rest, or is it Java? It's more about embracing all kind of inclusive type of approach. So you should be familiar with those things, at least at the level where you can freely communicate, at least understand the outcome of a particular activity in a particular discipline, right? And again, as I said, your questions are welcome. Put your question right in the questions pane. Okay. So data scientists or anyone working in the data processing field should be tasked with a number of things. So projects are quite diverse. Definitely business drives. Every company is business driven, even though some people say we're technology driven, but down the road it's all about business. How can you sell something? What kind of product? How can you satisfy your client needs? Even if it's software, down the road it's a business decision, right? You might have an excellent product which requires some tweaking, probably which would require an additional 6 months, but business would definitely just walk in and say, no, just ship it out. That's it. It might be subpar, but we just need to survive because our competition is very active in this field, right? So work is business. If you're not business, if you're business, you're fine. I'm coming from the technical background. I've been in IT for more than 20 years. I've seen lots of situations. And one thing that I've learned is that it's all about business as opposed to maybe a very polished, fine-grained solution. You can afford this luxury in some kind of corners of your organizations if you are eligible. If not, then go with the business decision. So you'll be involved in priming data, cleaning up data. It's kind of a dirty work where you have to kind of roll up your sleeves and just really get dirty. It's unavoidable. If you want to have something that is suitable for building your statistical models, for your machine learning models, you need to understand the data. And it's all about removing noise and retaining the data. So that balance, that sweet spot, is difficult to define, right? So it's something that you have to learn. Okay, the selection of statistical machine learning model, trying out or train those models so that you can produce an executable model. You will get something in the form of your data, train it. We're going to talk about this shortly. I'm not going to spend much time on this. It definitely would require a separate topic, but generally you need to transform your data, existing data, into a trained algorithm. so that you can apply that algorithm, that I would say that executing model to new data, and have the predictive capability in that training model. So you verify your model by running tests. Tests essentially, sometimes you just take your data, you split it into 20-80% or 10-90% split. You build your model and use the rest, kind of a small percentage of your data that you have to test your data to see how predictive your model is, the error rate, how accurately your model predicts a particular outcome, whether it's a label, class, and what's not. And validate your model with business. So when you've done it, and again, it's very important to have business as close to you as possible. Business usually don't want to associate themselves with all those kind of technical things. They would kind of not comfortable because technical people, they start kind of throwing those terms, you know, kind of machine code, JIT optimization, garbage collection, policies and all that stuff. But business needs to be kind of very close. So business and technical folks should be very much aligned. And validation is very important. We're going to talk about this shortly. Software engineers would help you essentially roll out your project in production. And your applications would probably solve a number of practical problems that you are currently facing, whether it's fraud detection, maybe correlating data, applying spam filter, and what's not. So examples of data science projects, the correlation models, maybe sometimes kind of recommendation system, predicting user choices, do cross sales, just finding out who's the audience, just trying to figure out the preferences, sentiment analysis. It's just unbelievably how much you can do with science projects. Right. It's important if you are working for a particular company and you are rolling out a new product and you would like to get feedback. It's important to incorporate that customer client feedback into your system so that your feedback would immediately give you insights into where and how you can improve your product immediately. The faster, the better. Right, so it's kind of Bill Gates once wrote a book like a while back, Business at the Speed of Thought, or something like that. Good read, dated, but all the I guess ideas was there. So customer segmentation and what's not. So gotchas. Those gotchas are unavoidable problems that you might find yourself entrapped. You can stumble over those. It's not removing information noise, right? If you delegate it to someone else and say, you know what, I have extremely capable system which would crunch all the thing and it would sieve through the data and would find the nuggets. Possibly yes, but there is always a chance, and according to Murphy's law, if something bad might happen, it would happen. And usually it happens when you do a big demo and there is lots of folks in the room and you kind of mess up your project and possibly your career at the company. Gigo or Geigo, whatever you like, is still valid. Sometimes if you have some people with a PhD in statistics, that's what's happening now. Lots of people from academia jumping on the bandwagon trying to share their expertise. Just essentially they're looking at greener pasture in the data science field. And those people bring in the baggage of their kind of academic type of background, which is absolutely fantastic, excellent. But when they're fronted with kind of frontline projects, like real life projects, which is just happening right now, we don't have time to really ponder about it, maybe just have a discussion with colleagues. It should be just done, I don't know, like yesterday. And sometimes the mindset gets in the way. So they go much too deep on the statistical side of things, just trying to fine-tune all those things. It's unavoidable. They have that scientific approach, but that scientific approach, which is similar to hacker mindset, should be kind of a balanced off. Hacking is scientific approach done fast, so to speak. It's kind of cutting corners. You just get the job done. Just hack the system. Just make it work, and we will figure out the details later. It's important to see the big picture. What are we trying to achieve, right? Are we looking for that proverbial, I don't know, drop in the ocean, or we can just see the ocean and get the sense of how salty it is, and is the temperature going up or down? And one of the biggest problem in data science is the inability to communicate with business and other stakeholders. So they become sort of an isolated, like ivory tower, if you will. And they sort of doing things on their own. They just having a whale of a time, kind of happy campers. And essentially, they just enjoy time playing with those models. It's quite addictive. But what needs to be done? There should be some iterations, like name it whatever you want. I don't know, like Scrum, Agile. Essentially, there should be touch points. There should be a plan. There should be a roadmap. What we're trying to achieve with specific deadlines, times, and so science is because science just has this kind of a flavor to it, that it's about just free, I don't know, will and free experimentation. It's not like that. Data science is about running things to solve immediate problems. Gotchas, sometimes when you produce an output and you go to the business, and business say, yes, we know about all that, tell us something that we don't know. And response to would be, no, it's not exactly what we expect, and you can spend lots of time just trying to maybe disprove or prove it otherwise, and eventually you will end up having that response number one. Yes, we know that already. So that's enough, I guess, for me kind of preaching this type of a business side, because that's what really I've seen people who don't do that, and they kind of jeopardize their career. So that's important. Just be aware of those business circumstances. Okay, so moving on, data analytics lifecycle. It's a big slide borrowed from one of the InfoQ presentation. A while back, it's an old slide, but it has all the elements. That essentially, it starts on the left, and we progress towards the right. You see that guy kind of stand alone. It's probably a business analyst who performs model validation. And eventually, you've got an accepted model, which can be packaged as a product deployed somewhere to work on real data. Okay, so that's the flow. So we will start kind of going slowly, and discussion that follows would be touching on those points. Definitely, we need to know what data we need to acquire. Right, so usually if it's JSON feed or some data coming from sensors or the Internet of Things, whatever the case might be, you need to know what kind of data you need, right? So you need to minimize waste or noise right at the ingestion point, at the data when you acquire data. Right, so it can be external data, operational data of your running organization. It might be your weblog files. So data integration is essentially just putting everything together, creating a stream of data, or maybe just a batch sitting somewhere. You need to start cleaning data. That data priming is very important. You remove noise, outliers, and in many cases it's quite obvious. There might be a problem. Sometimes under heavy load, logging might start producing kind of bizarre output. You're losing timestamps, and essentially you need to prime your data, remove all the outliers, and make your data as clean as possible. So there is a number of techniques, and we're going to talk about some of those shortly, right? And we can essentially start producing some reports on that clean data. Right, a very basic one. Essentially, we would do some sort of a select statement running an existing system, or maybe using Hive or Impala. Your data might be sitting in Hadoop or any other data lake in your data warehouse. So dimensional mapping, building all up cubes. But for data science, we are moving towards the right, moving to the right side of things, kind of to the east. We need to start feature selection. So feature are those properties of your data, attributes that you would like to select, and because you believe those are more important than others. If you're in the health industry, you might collect data which might have thousands of those properties, blood pressure, heart rate, and what's not. And feature is one of those parameters. And you need to select if you want to create a model to predict a possibility of a particular disease, or see how efficient a particular treatment is by just looking at those properties. It's very important. So data sampling helps you to extract maybe manageable subset of data out of millions, potentially billions of reads. And then you start essentially processing data, like modeling, trying to perform the match between the problem domain and the data analytics model. Is it classification, clusterization, supervised, unsupervised learning? And then you start building the model and run it at this point in time by business, or doctors, or someone who's a subject matter expert who have no idea how you achieve that, but essentially they would be able to tell you, yes, we know that, tell us something that we don't know, or that's an interesting point, can you drill down? So that's where the activity of data science happens. But also, cleaning data is very important. It's data engineering, but data engineering actually paves the way for a success in your modeling. So basically, all those steps or kind of phases in data analytics are listed here. So we discover data. Essentially, it's not about just discovering data. It's about acquiring data and have that data collection point at the right place to be turned on at the right time. So we perform data harvesting. So essentially, it's extracting those readings into something that is translated into a record, an event, physical proof of data acquisition with some metrics. Data priming, it's about cleaning, model planning. So now at this point in time, you start thinking about where pure data science, I would say. So before that, it was more of an applied data science, right? We're talking about applied data science, not pure data science. We're not going to spend the rest of this presentation to go in all those models. I guess it's just not possible, but at least giving you a bigger picture of what is involved. Model planning and model building. So at this point in time, essentially, you would use one of the languages, systems, and algorithms to start building your model. You build a model, you test it, and then you need to communicate the results. Again, very important. It should be kind of a capital letters, kind of uppercase. Production rollout, everyone kind of waiting for bosses to tell you thank you all. So data discovery, I guess it's nothing really that you need to know other than that's just you need to know the sources. I guess in terms of capacity planning, you need to understand the capacity of your existing data lake or data hub or your storage capability. So are we talking about gigabytes, petabytes, or terabytes? When you start acquiring data, you need to have all that in place. Of course, you can, I guess, organically grow as your data volume increases, but you are better off to be maybe a little bit ahead of the game, so that you have maybe 3 or 6 month expansion horizon where you essentially can accommodate that growing data. Everything might be okay at the initial assessment of your data sources potential volume, but you might have something like a hockey stick, a very sharp rise in the data acquisition rates, and you might be blown out of water. So be prepared for that. It's important. Of course, what you can do, you can put, I guess, some sources to the cloud. Cloud is cheap, cloud storage is cheap, and it's reliable. And if your data is not that sensitive, and you don't have any restrictions, no federal or state agency or provincial agency would come knocking at your door saying you're not allowed to do this, we're going to sue you. So if your data can be safely uploaded to the cloud, that would be one of the venues, so that you can eventually catch up with your on-premise storage capacity. Usually what people do, they start building a Hadoop environment, maybe with 100 machines, maybe 200 machines in a cluster. And every physical machine has multiple hard drives attached to it, and you can easily achieve petabyte level at this point, right? And you can always compress the data. Your data might, usually data acquired in text formats with lots of repeated data can be compressed quite efficiently. So there are formats for that, like Parquet and what's not, and you can, I guess, get by for another maybe 6 months before you acquire new machines. And again, the cloud might be a solution to your problems. Just upload the data, pay some extra data for storage, but it's pennies compared to what you might incur if you pursue that on-premise type of storage. Data harvesting is an interesting topic. Essentially, it's not about translating data like bit streams into data that can be meaningfully processed, right? So we're talking about ETL, extract, transformation, and load of your data. So data is extracted from outside sources. Just give me a second. I'm sorry about that. So we need to transform data so that we have certain profile of expected data. We have specific operational needs. And for that storage, for the backstore, people usually gravitate towards using Hadoop or any other system, or maybe even relational databases. RDBMSs are great because they already give you the storage and the processing engine. SQL is something that is ubiquitous. We have, I guess, experience. SQL is so natural if you spend some time just working with those. But it's kind of limited in what you can achieve. Relational databases are not particularly very well suited for horizontal scaling, even though you can do kind of replication, and big vendor would just tell you, no problem. We can do, I don't know, just sharding and horizontal splitting across machines. But it comes at a cost in the form of money, in the form of maybe losing some inner join efficiencies. And people are just going towards NoSQL, Hadoop. So that's something that probably you'll see more and more. And by the way, those who have joined us later, as I said, we will have a short break at the top of the hour for about 5 minutes, right? So that you can, I guess, grab a cup of coffee or use it more towards your needs. So data harvesting can be supported by any of those systems. It's kind of apples and oranges. It's a batch and streaming. They're not equal. They come from different domains. I just put them together so that they give you at least something that you can start by. Right, you might recognize some of the systems, maybe all of those. So essentially, the above systems listed here have some additional capabilities for data transformation ETL. Others are just very straightforward, like Scoop. It's just batch loading from relational database into Hadoop, right? Flume, same story. There will be 1 or 2 slides on every topic, right? But generally, just don't be too, I would say, just think about it as that mixed, kind of a mixed company. It's apples and oranges and kiwis, lots of different things. But essentially, they help you to bring the data into your system. And some of those would give you some ETL capabilities where you can essentially group your data, you can split data, or prepare your data such that your model building for your pure data science projects would benefit from. So Scoop is a command line tool. Pretty much all the tools are written in Java. That's a common kind of language. Some of those more advanced. The Scoop is pretty straightforward. Essentially, it allows you to effectively move data between your RDBMS, whether it's Oracle, Microsoft SQL, and Hadoop, and back. Import-export type of operation. So they come with JDBC drivers. Pretty much all the popular databases are already provided for. Here's a command of importing data. The Scoop import operation is about extracting data from the source database, like in this case it's MySQL, and importing data into Hadoop or Hadoop file system, HDFS. Right, so it's very straightforward. So you designate your database, you connect using the JDBC URI, specify the table. Of course, you need to have permissions to access, and you specify location, target location on HDFS. It's important at this point in time to tell the system what would be the delimiter for the fields. So you should be kind of aware that if there is a comma in a particular column as attribute of your MySQL table, then it will be a problem. Those delimiters are very important. So when you ingest the data on HDFS, then you can create schema on demand. So that your schema, whether you create an Apache Pig, Hive, or what's not, it would require you to specify the delimiter which you would like, which system would use to horizontally break your data into attributes, so that you can swap columns, so that you can run queries and what's not. Okay, so that's important. Flume originated at Cloudera. By the way, one of the guys who was working on it is Doug Cutting, who was the tech lead on Hadoop project. They recognize the need for something like Flume to get the data out of a particular source. It might be an application, it might be a log file, it might be just like a streaming system, and load the data in fault-tolerant way, so that if something fails, then the system would not break the flow, right? So they have production integration. I guess it has lots of, I guess, configuration properties. It supports Hadoop formats. This is very important too. So text files are not the only format used on Hadoop. Avro format, sequence files, JSON, Log4j. Avro is an extremely popular format for interoperable solutions, where you can create applications using your language, be it Python, be it C#, serialize it into Avro, and that Avro can be read by another system. It's kind of a protocol buffer used by Google. So Google have this, they have this requirement to have a way to interoperably communicate between their used languages, C++, Java, Python, and Go. So Avro is the response. Okay, so there is more like syslog messages for security, and you can tail log files, and Flume has some enqueuing capabilities so that you don't lose your data. Here's an example of configuration file. Flume uses agents. You can chain agents into type of workflows. Essentially, it's a JVM which reads data from the source and pushes it over to the sink. And every agent gets configured like this, shown here. So we have, I guess, hopefully you can see my pointer. So when you see this bind and port, essentially it's a socket server. So this agent essentially listens on that port, and whatever comes on it, it would get this. The expected type is Avro. It's default. And what it does for the sync, it outputs data to HDFS. So there is location, HDFS path. That's it. Some additional, but essentially you got the idea, right? We've got source, we've got sync. The agent actually pushes the data. If something just doesn't work, it would have the ability to kind of enqueue messages until they're flushed. Apache Kafka is another system which is kind of probably more powerful than Flume because lots of thought went into really creating really scalable platform. Originally developed at LinkedIn, and then those developer folks just realized that they can, I guess, get a more interesting application of their project outside of LinkedIn. So they just moved out in their source files. You will still be able to see that, like John Doe at LinkedIn, the author. Kafka is, in essence, just distributed commit log. So there is a file on the file system, and data is just stored on the file system. There is a great deal of efficiencies that they were able to achieve by just reusing some of the Linux kernel's recent additions, like send file, which essentially just bypasses heap-u application. You just move data from socket. You just instruct the system to move data using input-output from socket to file. Usually you go through, if you use Java, in order to process data, to move data from socket to file, you need to read the data. You need to bring the data into Java process, into the image, on the heap. And then you would essentially push the data through that heap into a file. But now Linux has become so, I guess, sophisticated. They allow you to just delegate this thing to the kernel level, where things are happening near real time, essentially real time. you've got gigabit Ethernet, and you've got SSD drives. Essentially, it's just big fire hose. So they're just using this to achieve those millions of messages per second. And that's a real deal, meaning that that publish-subscribe messaging system that Kafka is essentially can answer lots of questions. And the output can be sent to any destinations if you want. So here's kind of a basic command line console message producer and consumer. So you've got a broker, it's a server which exposes a particular port, and you might have multiple producers, multiple consumers. You can have consumer groups, lots of optimization. If probably out of the box, Kafka might be a pretty straightforward system. If you start building a cluster, maybe you would need to get in touch with consultants who are specializing in this. But essentially, you designate a topic. It's a publish-subscribe system, and consumer just gets the message out. Right? You can purge a topic, but usually when you read the data from a topic, that message still stays on topic. You need to kind of physically remove it if you want to. And you can read, you can specify offset, what you would like to read. Lots of kind of smart, looks like there is one guy who was driving this, lots of people, but just mastermind is just one guy, and who came up with this name, Kafka, the German writer. Essentially, he was just, I guess, just proving the point that it's possible. NiFi, another interesting story. So we will have a break in about 15 minutes, so bear with me. We'll have a short break shortly. So NiFi is an interesting animal. That project originated at, believe it or not, NSA. And NSA released this project via technology transfer program. It's an excellent product. It's probably very nice to work at NSA if you can. Very nice system altogether. So that system is really enterprise, not enterprise, I would say, it's internet scale, right? So that's kind of something that if you would like to really listen to the world, if you kind of have nothing to do at work, then NiFi is probably a product to use. Original code name was Niagara Files, shortened to NiFi. So it has the concept. I believe there is just one slide. So let me just do some promo for NSA. In essence, you can think about this NiFi project as if it is a highly distributed enterprise service bus. If you worked with MS Series, MS queuing from IBM, or maybe, I don't know, Mule, project Mule ASB, it's exactly what it is. There are processors which can transform data, move data, accept data, like RESTful endpoints, I don't know, a reader from a relational database. And then you would have a possibility to apply some filtering, transformation, and output, spit out data and send it to either another processor to build that workflow. That's where it's very good at, or to persist the data. It might be file system, HDFS, you know, name it. The list of the processors is just mind-boggling, like I guess 200 or something. Same with the services. So a very extremely powerful system, and it has a fantastic UI, which is responsive. So you pretty much take your problem domain representation by just dropping boxes representing those processors, connecting them with links, and then the system would translate it into executable model. It's Java-based, so there will be a Java processor located doing the job as per the configuration. You can persist it, it's XML file, very nice UI, and it's responsive, as I said. So if bytes kind of start streaming, you would see those updates, how much bytes have been written, how many files have been processed, and things like that. All the statistics just in one console. Very powerful system, highly configurable. And what's good about any streaming system cannot achieve all the properties. It cannot be fault tolerant. It cannot have high throughput and be consistent. All those properties essentially, there should be a trade-off. And NiFi nicely gives you that intelligent choice to select between tolerancy for data loss and guaranteed delivery. Depending on the tasks that you have at hand. Sometimes you might say, yeah, I can tolerate having maybe 5% of data being lost. It's okay. I can figure out the rest by just, I guess, looking at the data that I have. What's good is that you can, I guess, put it on a hiatus, kind of on pause for a second, modify the flow and reapply it. Back pressure is a feature to essentially throttle down the source, saying I cannot do it. Just shut up for a second, let me process the data. And usually it's done in a nice way, right? The most extreme case would be kind of a throwing 503 error. Like it's a RESTful endpoint, I cannot take it anymore. That's it, 503, server error, so it's your problem, not mine. Or if it's socket connection, then, or the client actually sends a request, you can essentially create some sort of a gateway just limiting the rate at which you process so that the queue that of unprocessed backlog is essentially transferred over to the client. You're kind of pushing out, saying, you client, you're going to choke me, you're going to choke first, right? So that back pressure is, has a number of, I guess, practical implementations, but essentially it's a very popular way to preserve the system sanity. Okay, so Apache Flink, it's a project developed jointly by 3 German universities back in 2010. Right off the bat, I can tell you that it's competing with Apache Spark. So Apache Spark is might be winning because it's a local domestic product, even it's at Apache. I guess lots of time and money has been spent on training people, setting up Spark. But in fact, Flink is doing the same thing. They've got Scala. If you look at the codes that you need to write to process data, they perform transformation of data, not only just receiving data and real time at high throughput, low latency, but they also apply transformations. So they've got flat map, they've got map, they've got swap key, all those things that Scala and Spark they boast about. Okay, maybe they've got even Mark Odersky, the creator of the Spark of Scala, working for them. I don't know. It has some of the features that are very attractive. I've seen some of the metrics comparing kind of some load test results, comparing Spark with Flink and Storm, and Spark is not there. And they just break very shortly under heavy load. Storm and Flink, they sustain the throughput until, I don't know, like millions of records. Okay, so I'm not doing any promo for them, but it's a great system. And it looks like if you look at Amazon Web Services, those guys, they really after the money. If business needs something, if the client is client-driven technology out there, they've got Flink already. So when they do, that means that some people are really asking for it. So they maintain state. They essentially have lots of properties that you might consider appealing to you. Documentation is good as well, but you see that it's kind of not really pure English. It's kind of has German flavor. Data priming phase, I guess removing outliers, potentially augment or enhance your data, right? Data normalization, It's not a normalization where kind of have a normalized form in SQL. It's about bringing data into a specific kind of a scale, scaling data, not in size, but scaling in values, so that you bring them maybe like if you got a range of your data between minus million and plus million, essentially you bring it to the 0 to 1. Right, and those fractions would be accounting for that spread of your data. It helps with algorithms, because algorithms, when they assign a weight to your data, they consider the actual absolute value. So that data priming is important, but we already work on the data which already sitting somewhere, data at rest. So before that, it was maybe data at motion or data in transit, whatever the term is more suitable in your context. But all those kind of priming, cleansing begins at this phase. You can also remove outliers and maybe perform augmentation at data harvesting. So it's up to you how you want to do it. If you can afford kind of spending some time at the data harvesting, you essentially pushing out some of the responsibilities of this phase upstream to the closer to the data acquisition point. So selecting model, machine learning algorithms happens at this phase. It's important to extract sample of data and start working on actual data that you have. Proof of concept type of project. Again, it's more of a scientific science project. You don't need to boil the ocean. You need to start with something small, get the taste of your data, just understand what can transpire if you do that, and then carefully move forward. You build your model, train it. It's important to identify, usually training is a time-consuming phase. Your system would need to crunch, find all those kind of patterns, associations inside your data, and do all that stuff. But runtime is usually faster, particularly if you do something like random forest type of classification. Right, but you still need to be aware of that. If you want to deploy it as the real-time system for like fraud detection and maybe cross-sell type of operations, procedures, you need to know the runtime profile in the form of CPU utilization, storage, and generally understand what might happen if you deploy it at runtime. Communicating the results, use as much visuals as possible. So if you just produce Excel spreadsheet, it's not enough. At least do heat maps. Right? People kind of really start understanding things when you start comparing, showing some aggregates. Just treat your audience as very busy, very kind of a short attention span, people who have probably, I don't know, 4 minutes while you are going on the elevator up or down. If you can explain it, just capture their attention. If you really see the value in your model, do that. So communicating on results is not good. Most people are not very good at it. So probably you would need to have someone who is has a flair for that, who has that talent. It's very difficult to come by, but you probably know someone who can see offset by 1 pixel on the picture, right? And you need to have those people on your team. So visuals are important. Pie charts, bar charts, maybe some moving data, maybe some animation, even better. Production rollout, I guess it looks like you've essentially sold your project and you just deploy it. Okay, so, but don't kind of relax too much. There should be a warranty period within which you should be able to enhance, improve your system so that you have a continuous loop back. Okay, so let's break for, let's say, 7 minutes or so that we can continue with the next chapter. So it's a break, okay, 7 minutes, and we will get back at that time. Okay, continuing. So now we are moving towards the actual data science algorithms and some of the methods used. So data science is not limited to kind of using those analytics methods. There is more, but I guess they're quite representative. We do classification, we do clustering, supervised, unsupervised learning. So those algorithms that you can see here, they help you to solve problems in a specific problem domain. It can be as simple as Monte Carlo simulation, or time series analysis, or regression analysis that you can do with Excel or any other SAS or SPSS system, whatever you use. Some of those algorithms can be, I guess, run on your laptop, on your kind of a standalone machine, desktop. Others have been ported to run on a cluster of machines. So Spark, for example, is a good example of a system which allows you to run, for example, k-means or decision trees on a cluster of machines, whether it's Mesos or Hadoop. By the way, Flink also catches up the bundling on machine learning or data science algorithms on top of the Flink runtime. So supervised and supervised learning, that's the dichotomy which separates two big types of algorithms. Supervised learning requires your involvement pretty much. Unsupervised learning, when you give very basic kind of inputs to the machine, you give the data and the system would perform the operations based on the insights that the machine can figure out. That's probably machine learning in its purest form. Supervised learning requires you some kind of a classification, just adding labels to data sets. Right, and unsupervised learning is real machine learning, and it's, as I said, a true one. Usually it performs grouping, clustering, and when you do the clustering, essentially you have create a model that it can be used for classification. Okay, so that's how things are structured. Supervised machine learning are listed here. Decision trees are very popular ones. Naive Bayes algorithm as well. Regression is supported by Excel, so you can start with Excel. Build kind of some trends to understand what would be our sales next month based on our historical performance. Unsupervised, it's all about clustering. So number of algorithms. There is more, for sure. I guess it's just a very quick, listing the algorithms. So now let's take a look at those systems that are available for you to actually perform data analytics. You've got choices. You've got all those things listed here. Just to mention a few. There is more. And that's a recurring theme I mentioned at the beginning of my presentation, is that today we should be thinking in terms of and, not or. So we are talking about, I need to know Python and potentially maybe Big or Spark. It's not about what shall I learn, is it R or is it Python or is it what? No, it should be probably something but generally a system that you have selected and you've used for some time and you have become proficient, it probably would be something that you should stick with, right? You can just sporadically step out of that comfort zone using other systems. But what's interesting is that if you start working with multiple systems, you would start understanding your problem domain better. There will be one slide later in the presentation, just an example how you would compare one system against another. But essentially, in terms of like pig or hive, even though there will be one or two slides on each topic, they are not difficult to learn. Hive is SQL, pig is kind of a TSQL type language, PLSQL. Python is not difficult to learn. It's one of the simplest languages probably. R is a little bit of a different animal, and Spark supports Python, supports Java, Scala, and R. And Scala is one of the languages that people, I guess, embrace, even though it requires a steep learning curve, but for data science projects, for ETL, machine learning, you don't need that the whole gamut of Spark Scala capabilities. You can pretty much stay within some idioms that you can reuse over and over and over again. So pretty much you're a Scala programmer, but at very low level, and that's enough. That's interesting. With R, you probably would need to really understand this language. So let's take a look at R. R might be right away, right off the bat, can be a replacement for lots of systems that are currently used, and you have to pay licensing. So if you're someone who is responsible for managing those licenses, and you kind of see that you can achieve some savings, switching to R might help you in some area. It's a interpreted language. It's not very fast. It's single-threaded. What else? In terms of negativity, as soon as possible. So garbage collection really not up to the job. You will have to do manual cleaning up. But so that's so much for that negativity, right? So the good part is that it's quite established, right? It has history. You can find lots of people who know R very well. For computational intensive task, R leverages DLLs and ActiveX controls that wrap up C, C++, Fortran routines, believe it or not. So essentially, there would be call out to the native code. The job would be done there, and the response, the output would be redirected back to R. Statisticians love it because it's kind of arcane. It's so compact, so concise. Sometimes it's arcane. That's what statisticians like as well. So it sometimes has idioms that you might say, yeah, it's kind of an interesting language. Nice slide which compares R versus others, kind of us and them. So R kind of on one scale of that kind of a balance, and on the left we've got lots of others. So we've got Python with SciPy library, we've got SAS, F# from Microsoft, SPSS, and essentially R can give you a good balance, and it has features that can, I guess, be used to solve problems in many problem domains. Mind you that it gets distributed as GPL, so your legal might have some needs to take a look at it. R is superglue, so it has thousands of various libraries, probably one of the richest out there. And the same algorithms has multiple implementations from different people, right? And what's interesting is that those libraries, they come, packages, modules, they come from people who have background in statistics. That's a very important point. So they really put their reputation on the line. So you should be assured that if it comes to statistics, those modules have been tested in and out by those colleagues, by themselves. Essentially, it's kind of a top-notch, kind of a high-quality libraries. Not everything, so when it comes to maybe reading data or pushing data out, interfacing with a particular system, that's probably not as good as, but real statistical machine learning libraries are very well written. Maybe not that fast, so mind you. So number of development environments, so I put specifically the rest in small fine print. So if you want to, you can explore, but the recommendation is to use RStudio. So RStudio comes with two editions, desktop, where you just deploy RStudio, point to the R binaries, or you've got RStudio server where you have access to the R engine using web browser, and you can collaborate with your offshore teams. So that's what RStudio UI looks like. It's an integrated, essentially, it runs on any supported platform. It has built-in graphics on the right. It allows you to introspect the memory. It will give you a list of those objects which you can delete. You will act as a garbage collector yourself. You can fetch data, you can install data packages from the CRAN that I should have mentioned this. It's not here. Essentially, they've got the repository of modules, comprehensive run R language archive, CRAN. And it's very reactive, so you can introspect frames and all the structures right away. So that's kind of what gives you a sense of what you can see. Lots of beautifully done things. If you start using it, you'll probably get addicted. But again, it has some limitations. It probably would be more likely limited to just one machine, even though some people claim that they can run R on a cluster of machines. But for that, you would probably be better off to use Python or something else. Again, R, excellent tool. So they've got all the statistical machine learning algorithms. Not everything, like in terms of like real machine learning, but as we know, like image recognition and language, kind of voice to language type of transformation, like what Google does. But they have all the majority of algorithms that you would expect a system to have, right? And it's very nicely done, and lots of documentation. A word of caution: sometimes documentation, every package comes with documentation. And sometimes when you read documentation or you see the examples that they're using, I'm not an R kind of expert, but I worked with it. But sometimes those examples are written by statisticians for statisticians. And you need to kind of reach their level to start understanding what they're talking about. In many cases, they don't care about explaining things. They just do reference to something that they know. And it's kind of requires some discipline on your part to really grow up to that level where you would become kind of in the knowledge, in the know. It's kind of a slang argo, if you want. R was designed right from scratch as statistical processing language, statistical language for statisticians, and it's reflected in the data structures that they have. No other language, like as we know, like C#, Java, Perl, Python, out of the box without add-ons. They don't have those kind of data frames and matrices. They've got probably vectors lists, but not as elaborate and diverse as R has. So data frame is probably one of the most important data structure, even though matrices are very well suited as well. But essentially, it's a kind of relational database table. You've got a matrix where you've got named columns, and essentially you can apply certain operations to a data frame. It's a main structure. It's very similar to what you would have in SPSS and other systems. And by the way, I guess Python, Spark eventually adopted the same approach, data frame. So they started moving their machine learning to data frame centered processing. So data frame, out of the box, it's really the centerpiece of the processing. Easy to use, has very nice representation. In RStudio, you can do sampling of every R data frame structure. Also, R comes with the API and procedures, methods around all those concepts that are needed to perform statistical type of analysis, data analytics. For example, matrix algebra, something that you would in another language would have to implement yourself or borrow as external library, that functionality is built in. So, for example, if you want to do inversion, matrix multiplication, transposition, you've got operations for that. And you can assemble matrices by row, by row, or by column. You can merge data. It's an extremely powerful concept. Essentially, it just abstracts all the complexities that you will have to dive into in another language to implement it. R just gives you those constructs right away. So it has the data structures, and it gives you the methods to operate on those data structures in a very nice, easy way. And sometimes it's just unbelievable how easy you can do a particular data engineering type of thing. You can extract data in a column, column-wise or row-wise. You can combine data by columns and by built-in graphics. It's quite capable. Gives you nice way to quickly create just turn up those very visually appealing graphs. There are some external libraries which do even better job, but in many cases you need to do that preliminary data analysis, data exploration. So you get a sample of your data, and before you start building your model, you need to do some kind of understanding, getting to know your data. Data exploration is done with visualization. R has it built in. It's very powerful. You can export it as a PDF, as an image. It's one of those things that you could use to, I guess, sell your project to your stakeholders. Data import and export supported. Lots of libraries, as I mentioned, lots of interfaces or drivers that allow you to communicate or integrate with various systems. So you can read, for example, Excel spreadsheets. You just need to load the library because, for the most part, the core R that is available when you launch R doesn't have all those extensive features. You need to bring them in by using the library procedure. So that XLXS library should be, its module name should be already pre-installed. If you run it, then we'll have an exception, which would probably be quite informative to tell you, just download, go here, and install it. Okay, so you've got integration with a variety of systems. Statistical packages, they output files in a specific format, and R can give you. So if you would like to start experimenting and you already have one of those systems, just download, install R, no strings attached, use it, and see for yourself how you can save money, because it would be transferable skill. If you specialize in a particular statistical package, probably you're limiting your choices. R will open doors for you. Data export, so the opposite, I guess, push is also available. You develop your models in R, and then you save them so that you can import the data into any of the system of your choice. Again, as I said, if you have any questions, just put your question in the questions pane, and we will also have a Q&A at the end of the presentation. So NumPy, SciPy, Pandas, Python, Matplotlib, scikit-learn, all those packages are extensions to Python. Python is an extremely straightforward and I would say intentionally done simple. It's extremely powerful. There are lots of things that people love and hate about Python, but Python in itself, it's just kind of a toy language, you might say. It's not fast. It doesn't have that kind of extensibility. It has all the good features, but people are attracted to it, but they quickly realize that I guess the data processing power is very kind of limited. So for that, people just added those libraries to really extend it. So for example, NumPy, this is a module written in C, which allows you to dramatically improve the speed of data processing, which gives you everything that you can find in R, like multidimensional arrays, matrices, and routines. So SciPy builds on NumPy, and it gives you algorithms for data manipulation, visualization, and what's not, which already is available in R. Pandas gives you data structures, procedures for practical data analysis, finance statistics, and what's not. R already has those data structures, right? So essentially, Python is catching up with R, which has all those native capabilities, by adding libraries. But the good thing about Python is that you can find, I guess, many more people familiar with Python and quite proficient than in R. And in many cases, you would probably have someone who doesn't know very much about statistics and data science, but algorithms are already available there, like SciPy or scikit-learn. They give you those needed libraries. It's just a matter of understanding. Documentation is fantastic. There are other ways to extend Python. And when you want to have all those things in just one package, download Anaconda. So Anaconda bundles all those things and gives you more big package. Python is a good choice in that Python is supported by many systems. Like you can create streaming, you can create MapReduce jobs using Python. Spark supports Python. Python can run on its own. Multi-threaded in some cases is supported, but you are better off to maybe start doing using Python on local machine, and then when times come to process data on a large scale, you can use any of those engines like Spark, MapReduce to run your MapReduce jobs using Python on a cluster of machines. So that will be kind of a single-threaded processing, but there would be hundreds, if not thousands, of Python programs running, essentially creating thousands of threads of execution and improving the throughput of your data science algorithm. Apache Pig. Some people don't like the name, but it's just the tradition of the Hadoop, which is a reference to an elephant, Doug Cutting's son's toy, a yellow elephant. So people start talking about Pig and Hive, Impala. People at Yahoo who developed Hadoop and MapReduce, Doug Cutting, one of those folks, they realized that to be productive, they need something. They need to give business analysts something which would shield them from the complexities of MapReduce. Even though it's not really difficult, but you understand to achieve a velocity or shorten the development cycle or improve the life style of business analysts so that they have some time for to be out of work, some time for life. They need to have a tool that would use MapReduce under the hood, but they would be interfacing with that engine by using something that they would be familiar with. I believe there would be a slide, yes, which just shows a sample of that program that does the job. And they developed Apache Pig. Shortly, they donated it to Apache Software Foundation. And Pig, by the way, is bundled with every Hadoop distribution, whether it's Cloudera, Hortonworks, MapR. You can find it on Amazon. You can find it in many places. Excellent, very easy to use. And even though MapReduce is now deemed as the kind of deprecated type of technology, it's slow. It has done its job. It has seen its heydays, but now it's kind of on a decline slowly. Pig can run also on Apache tests or Spark execution engines. You can get multiple times better performance running on those engines. So here's an example. I'm not going to spend much time on comparing. Essentially, we've got a Pig Latin script. Pig Latin is the language that you can see here. And the functional equivalent SQL statement is shown below. So what we are doing here, we're just trying to produce a very basic report by listing a year and the maximum temperature for that year. So there's in a country is weather observation system. There are weather observation system stations which collect the data, and they feed the data to a central repository where it gets accumulated. And you've got a huge database of the data. And SQL can perform that task for reporting by just grouping by year, and within every year, after applying the filter in the form of the where predicate, where it would filter out data by temperature or by quality, we would produce a 2-column report. Okay, simple, efficient, and very fast. You put an index here and there, and but Pig Latin script kind of does the same thing, but in a more kind of procedural type of operation. SQL is kind of 4GL language. It's more of a functional programming language, where Pig or Pig Latin is more about being procedural. Just every, like the filter is the where clause. If you want to do group, it will be a separate clause, separate statement, and eventually you do for each. For each will be iterations through those groups and performing, finding the maximum. It supports inner joins. It supports a great deal of diverse functions. So it's really a good idea to spend some time, I would say 1 day, at least 1 day, maybe more, maybe 2 days to learn Pig inside out. So Hive was originally developed at Facebook, who were really struggling with the data influx that they were experiencing. Oracle didn't help, a cluster of MySQL servers didn't help. Eventually they learned about Hadoop, but I'm not sure about if they were aware of Pig or they wanted to take it to the next level. So they developed Hive. So Hive essentially does the same job as Pig. It runs on top of MapReduce by giving business analysts and non-programmers, essentially executive type of folks, can run SQL as well, and to get the results running against Hadoop. Essentially, you've got SQL. That's the value proposition. You've got SQL, and you have a notion that there is a table of some sort sitting somewhere, which might be, I don't know, petabytes worth of data, and you run SQL, and you get the results as if it was a real table. But in fact, it's just not completely true. So MapReduce is becoming on kind of more on a decline. I guess it's going to stick until the thermal death of the universe, but generally there are other systems that are faster, like Apache test, Spark execution engines. You've got integration with Amazon S3, Hadoop, and other systems. So here's an example of how you would mount a schema on a location in HDFS where you've got 2 columns. Let's say we use scoop to extract 2 fields, from relational database, and we imported data on HDFS. Remember that scoop, Apache scoop discussion we had shortly a while back. And we have the delimiter tab between the columns, and the first column is literal, the other column is an int. So we create a schema using that DDL, which just remarkably similar to what you would see in the regular SQL 92 type of spec. We create external table. So external is a way to say, I would like to create the schema to represent that data sitting on that location on HDFS. It's a text file, tab delimited, give me that. And that's it. This operation will take you like 1 second, right? But then when you go to schema essentially gives you access to the actual SQL query capabilities. You can do grouping by, having, ordering, selecting columns, and what's not. Subqueries are supported, all the SQL constructs. Extremely powerful and fast too. You can do partitioning, you can do some optimization, indices are supported. So lots of things going on under the hood, but generally you should understand that analytics at a very kind of a high level, at SQL level, is possible. You don't need to learn anything. You just need to have access to that Hive console, to the Hive client. Right, so I guess if you're not familiar, you can add, I don't know, to your resume that you know Apache Hive. So that's enough for you. And so when you come first day on the job, just say, I need Hive console. Just give me Hive client. That's it. You can run those commands. So Spark is really interesting system. I guess Spark has been developed in response to the known MapReduce deficiencies. It's I/O bound, latent, not very fast, very robust, very reliable, fault tolerant, but it comes at a very big kind of price. Spark tries to address all those. They claim to process terabytes worth of data, but for that you would require really powerful machines. So more realistically, you would have, I would say, tens of gigabytes worth of data. So don't be hyped into that system. Okay, so Spark is designed such that it allows data science projects, machine learning, to be executed very efficiently. So they support that multi-pass iterative algorithms where you can process the same data over and over again. MapReduce is not very good at this. If you want to get to the source, if you want to get consultants, Databricks. Currently, Spark is bundled with all the Hadoop distributions, Cloudera, Hortonworks. Or you can use Spark as a standalone. It's an Apache project now. Used to be just US Berkeley AmpLab project. Spark is interesting in that it's not only good at the engine level, but it's also very good at the choice of libraries that it offers you as a developer. It gives you Spark SQL, streaming, machine learning, and graph. Again, not all the animals are created equal in this case. Probably the best application of Spark would be just its engine, which is very good, written in Java with Scala. Spark SQL is kind of a smoke and mirrors. You start with SQL, but end up using actual Spark. So it's just for those people who want to be attracted. It's just a marketing ploy, I would say. But Spark SQL is good at other things, like moving data using data frames in various formats, like in JSON. So it's kind of a misnomer. It should be more of Spark, I don't know, just generic data API, if you will. But they decided to go with SQL to attract people. A little bit of marketing. Streaming, as I said earlier, compared to Flink, doesn't really hold the water. It's just not really that capable system. It's good for maybe low to medium size of loads. It's good, not mission critical. It has some deficiencies, but it has some, I guess, use cases, so don't discard it. Machine learning is very good. Machine learning allows you to run those algorithms that we mentioned earlier, whether it's clustering classification, on a cluster of machines. So essentially, you've got potentially 100 or 1,000 times faster processing of a particular algorithm compared to your desktop implementation. They support Python, R, Java, and Scala. GraphX is good for graph-oriented processing. Lots of things can be interpreted and processed using Graph API. So common Spark use cases, ETLs, even though it's probably quite mundane, kind of not very kind of a Sparky thing, but Spark does it very well, particularly if you use Scala. Scala is very terse, it's very compact. Flink does the same thing. So Flink uses Scala, and you've got constructs. Scala is extremely expressive language. Data analysis, machine learning, risk assessment, graph, predictive analytics, text mining, there are libraries for that. So this is the list of, I guess it's later. Yeah. So essentially, you cannot get everything that you would find in R or in Python. Not all libraries or not all algorithms can be easily ported to be run on massively distributed platforms on a cluster of machines. And in that, you are limited to probably R or Python standalone. But in many cases, you don't really need that. You just need, I guess, to understand your problem domain. So when you understand your data, you might just take a sample of data. You don't need, for example, you've got correlation, right, between one column and another. You can use Hive or Pig. They've got a function which actually builds a correlation. And for correlation, it doesn't matter whether you run it against 100 or 1,000. Actually, I would say more realistically, over 1,000 records or million records. It would produce more or less if there is correlation, which is consistent across all the records, with some possibility of outliers. It will essentially build a very accurate coefficient, that index of correlation, that measure of affinity of data, whether it's 1,000, 10,000, a million, right? So if you understand those, you can always sample data, extract just subset of data. You don't need millions of records. And then you can use any of those APIs to pull data out of your data lake into your local machine, run R or Python, just get those metrics, probably prove them, just taking multiple samples, and produce a nice report, if you will. Okay, so it's a scientific method, kind of a hacking approach. Supported languages, primarily Scala is used, Java, especially Java 8. So Java has been dragging its heels for so long, and I guess Sun Microsystems, they were not interested in really advancing it. They just wanted to, I guess, they had a different agenda. And eventually, we arrived in Java 8 at the Lambda expressions, finally. And that's what Scala is all about. It's about functional programming. So you can build MapReduce programs natively. Scala and Java, I would say Java not so much. I would say Scala and Python, the primary languages. R was added, but R is only available on Spark standalone. It's not available on Hadoop as yet. Even binaries are there because R is a separate kind of a product. Python is supported, and many machine learning programs are written in Python. because you need to really experiment, quickly produce. It's interpreted language. It's not as fast, but you save your time at the setup and tear down cycles. Essentially, you distribute your program at source level. You don't need to compile Scala Java into bytecode, build jar file. It's much faster. And what's interesting is that they support all the libraries, like NumPy and Pandas. Everything is available for Python. Python and Scala. That's very important because some systems like App Engine, Google PaaS platforms, they limit you as to what you can do with Python. At the centerpiece of Spark, we've got RDD. It's a resilient data set, or RDD, which is essentially a way to recreate your data set from scratch if you lose it. Right, so there is a question, is R H2O a solution to add more threads? If R H2O, are you referring to a platform that the processing framework, H2O, or what is that? Sergio, I've not understand the question. To add more thread. Yeah, you can add more threads. There are possibilities. By the way, Mahout on Hadoop project, they essentially lost their battle to Spark, and now what they're doing, they're trying to develop R interface to Hadoop so that you can run. There is also R on Hadoop. There are lots of projects to make R essentially available to run on a cluster of machines. There are possibilities. Yeah, so I guess you can use any of the engines which would allow you to launch a single threaded application, whether it's in R or Python, give it a piece of data, just chunk your potentially extremely large data sets into chunks of data and feed that chunk to every single process running on a single thread. And then you should have a coordinator which would collect the output, perform some sort of reduce operation, and produce the output that would essentially represent that collective effort. So it's possible, absolutely. So RDD is a centerpiece. So you need to know, if someone asks you about what Spark is about RDD, and that would be good enough. Spark runs on a cluster, and what's interesting, they have their own cluster, which is not quite efficient, but the main target is Hadoop. Hadoop runs on Yarn. Yarn is a cluster resource management tool. You can also run it on Mesos. So essentially, those engines are scheduling, monitoring, and execution engines. They need to be driven by a master. So masters, there are multiple masters. So Spark is really humble. It can operate under various masters. That's important, right? So Spark has really good selling point that it's very diverse. It supports multiple storage types and cluster management requirements, right? So it supports HDFS, S3, OpenStack, what's not. Formats from Cassandra, HBase, I also support it. You see, so Spark essentially is just position itself as a system which is quite versatile. It gives you a set of libraries. Not all the libraries are created equal. So you would probably need to experiment with Spark if it's really good. Maybe you can take a look at Flink. It's up to you. But Spark looks like it has got lots of traction, lots of, I guess, buzz. Has been around for quite some long time. Quite a long time. So it's a great platform. Experiment with it. Just as I said, it's not about or, it's about and. So Spark maybe, and for certain cases you would need to use some other system. So machine learning packages, currently 2, ML and lib, and the break off happened when the data frame structure was introduced. So data frame has proven to be so, I guess, productive, helping developers to achieve a level of velocity not comparable. So ML is still available. it works, but I guess Spark original developers, they trying to push people over to MLlib, Spark MLlib. So actually it's the reverse. Originally it was MLlib, and the current is ML. Right, so that's they support, as you see, ML package doesn't have the diversity of the MLlib package. They're catching up. They want people to join and contribute more. So that's where things are moving. Spark is currently version 2. They changed certain internal implementations. They're still struggling with certain things. They have that optimization in memory processing. And sometimes if you don't have enough kind of physical memory, or if you have misconfigured, you accepted all the defaults and you are not paying attention to those details, you don't have enough, I guess, depth in understanding Spark. You would have lots of out-of-memory exception. Quite irritating, right? It's a great system, but as any system, it requires the proper, I guess, managing the proper, I guess, grade of gasoline. So here's an example of using Spark MLlib. It's a Python program which uses the k-means library. So essentially, we create Spark context. It's an API to the rest of the system. SC, that's the common abbreviation. It exposes API for interfacing with the file system and applying some transformations. So whenever you, for example, you load the file, like text file is the way to load the file from any of the supported storage. It can be S3, HDFS. You get an RDD. So that RDD is essentially a way to wrap up your data. Everything is lazily evaluated. Nothing is really happening. It's just the system just records. It puts on the stack of all the transformations, operations that you intend to, until you actually start processing. So we do map. It's lambda calculus. We essentially extract data by splitting data. That's a construct from Python. K-means, that's the core module which allows you to train data. Essentially, we are trying to find 3 centroids in your data sets. We've got 10 runs, 10 threads of execution. Epsilon, that's the tolerance level. And model is built, so it will take some time, let's say a minute. The model is built. You can calculate the cost. Essentially, it gives you some metrics to assess how accurate the system is, what is the error rate. And the beauty is that they've thought about this. How about serializing or saving that model for future uses? That save model.save essentially allows you to persist the data, again, S3, any of the supported file systems. And later on, when you would like to bring it in, so your work is not lost. Essentially, you build that model k-means, which has essentially that graph of some logic which they generate, and it gets serialized, showing the boundaries within which a particular feature would contribute to specifying the centroid. And it's kind of it takes time, but essentially that model, it's small and it's very fast. So when you load it later on from storage, you can run it against your data that come in, maybe real time, and perform prediction. So prediction would essentially will tell the system which cluster out of those 3 the data point belongs to. Okay, so that's the full cycle. Python API is there, runs on a cluster of machines, achieves, does the job. Okay, so same can be done in Scala and Java. Okay, so I guess this slide actually puts together some of the, I guess, properties of a system that you would like to use when you're comparing two systems. It's kind of 2 radical things, 2 sides of a spectrum. R and Spark. But just let's take a look at, just go bullet by bullet. So R is interpreted single-threaded. The good thing is that now R supports 64-bit architectures, meaning that your heap is not limited to 2 gigabytes. It has problems with garbage collection, so it's not really a garbage collection as we know, like in Python or Java or CLR. Spark gives you a choice of faster languages. Java, Scala, particularly mind you that Java, Scala, the essentially interpreted language, interpreted systems, right? But if you've got just-in-time compiler, if you've got that hotspot machine, virtual machine, after like 10,000 iterations or so, which is very similar, which is very prevalent in machine learning algorithms, the system would pause. It would take that instructions, that bytecode, and it would compile it into machine code. And then it would kind of create that process which would be connected to your Java process, and it would pretty much tunnel your data to that machine code, which would run as if it was real machine code, like assembly, like C. You can achieve this in R or Python. Spark handles, it has garbage collection, so you shouldn't be bothered about exhausting, overtaxing your system and getting out of memory exception, right? For certain things, there are certain optimization techniques available, such as the external tachyon-based caching system, so that you essentially avoid garbage collection process at all. Spark runs on a cluster of machines, right? So essentially, if your data is really big and data is properly partitioned, you can launch multiple processes. Essentially, every process would be a thread of execution. R gives you a choice. Even the same algorithm has multiple implementations, and they're top quality. Look at this as well. Spark has good quality, but I believe they might hire statisticians, but those statisticians kind of might not be as, I would say, actively involved in the statistical community. R on Spark is available, but for only standalone, and machine learning there is limited. Okay, so that's kind of one of those points that you would like, even though we use R and Spark, but at least look at those things. 64-bit support is very important. Right? The bigger the heap, the bigger machine you can get, and essentially you can cache a great deal of work on a single machine. Because when shuffling happens, shuffling just kills you in terms of performance. Okay, so we're a little bit ahead of our schedule. We are scheduled to run until 1:30, but I guess we've got more time for questions. Our offerings, WebEdge offers you a number of classes. Just 2 of those are mentioned here. Right. So yeah, that's it. So let's open Q&A. You know, the best way to have a question is to put it in the questions pane. I see the hands reason, but okay, so let me just try to unmute you. So, Ensan, go ahead. Ersan. Well, it's not going to fly. Sorry about this. Okay, put your question in the questions pane. Yeah, I guess raising a hand is not going to help. If you can put your question in the questions pane or in the chat, I'm going to pull out the chat and put your question in there. It would be easy for me because there is lots of background noise. I know that from experience. It's going to affect us. I don't see any questions coming in. Okay, one more minute. If there is no questions, then I guess we are done with this presentation. Hopefully you've found something that just appeals to you. Definitely it was just very high level overview, but I wanted to give you some sense of what might be involved. In many cases, it's not about just writing that program in Scala with algorithm and do the job. It's the whole pipeline, it's the whole workflow with data ingestion, priming, selecting the right tool, looking at the possibilities, comparing systems. There is a wide choice, and if you really want to become, I guess, productive, you would need to learn at least 3 systems, different systems. Okay, so so the way to go is to have R and Python background. I would say it's a good start. Yes, Sergio, it's a good start. Okay, Phil, thank you very much for your words. Definitely, Scala might be another choice, but Scala, for many people who don't have a formal programming background, might be a little bit of kind of a nuisance. Lots of kind of terse syntax, but it's really worthwhile. So when you learn it, it will pay off. Okay, so that's all time. It looks like we have no questions. I expected more questions. Yes, there are no other questions. So the question was, shall I use R or Python or both? That was the question. I said yes, both R and Python. Other question was just saying that about presentation. So I always welcome the feedback. If you feel like I missed something, or I don't know, if you would like to maybe hear more, potentially you might have a specific requirement. Like we can have a webinar specifically tailored towards your needs. If we have a repeated request for a certain system or just a topic, then just contact WebAge or whoever gave you information about this webinar. Send a link, so you can always contact our salespeople. Would be happy to help you. I cannot say that if you just have a very specific requirement just from 1 or 2 people, we are not going to really be able to just create a webinar. But if it's something that people really want to see in your organization, it's potentially you've got a project, let us know. So we'll see what. Okay, so yes, you are welcome. Okay, guys, that's all. I wish you every success in that data science. Hopefully, I've been able to convert some of you if you haven't. So, wish you every success. All the best. Bye-bye.